we're going to start our problem with a semicircle. Then we're going to pull the chord of this semicircle, and let's say that this chord has the length of x. Then we're going to take the upper segment of our semicircle just above the chord, and we're going to fold it as origami so that it touches the diameter of our big semicircle. And it will touch this diameter in such a way so that it will divide it into two segments with the length of 3 and 1, as you can see on the sketch. The question is, can we somehow calculate the length of the chord x? This awesome problem was presented to me by one of my subscribers, Antoine. And he stated that we are going to need all of our brain cells in order to solve this problem. So let's try it. If you guys are up to the challenge, you can always pause the video right now and then come back and check the solution. Alright, so let's solve this awesome problem. So first, I'm going to label the center of our semicircle as O and the intersection point as D. Then I'm going to label the vertices of the diameter of our semicircle as A and B. Now let's rearrange this for a better understanding, and let's have a look at the first fact that AB represents the diameter, and it consists out of segments AD and DB. So if we substitute their values from the sketch, we can get that the diameter of our semicircle must be equal to 4. But if we take a look at the line OB, you can see that this line represents the radius, and the radius is equal to the half of the diameter, so it must have the length of 2. Now the same thing applies for the line AO. This line also represents the radius, so it also must have the length of 2. Now let's take a look at the segment OD. This segment can be calculated as the difference between our radius OB and the segment DB, and if we substitute the values from the sketch, we can easily get that this segment must have the length of 1. Alright, so now let's clear our image a little bit and let's put our sketch a little bit downward. Now, let's complete our semicircle. And let's take a look at the circular segment which we folded. This segment was folded from the top part, so the top segment must also be equal to this bottom segment. This means that both of those segments are the part of the same circle. So we can easily construct the circle from our bottom segment, and this circle must have the same radius as our half circle, since it originates from the same segment. So, if the radius of our half circle is equal to 2, this means that the radius CD of our big circle must also have the length of 2. Now let's use the tangent of a circle theorem, which states that if we pull a radius to the point of tangency, the radius will always be perpendicular to the tangent line, and we can use this in our case. If you take a look at the line AB, it represents the tangent to our full circle with the center C. So, since CD represents the radius to the point of tangency, this means that the angle at the point D must be right angle. Now let's connect point O and point C with the line, and in this way we will form this really nice right angle triangle ODC. So we can use the Pythagorean theorem in order to find the length OC. So the hypotenuse OC squared must be equal to the leg OD squared plus the leg DC squared, and we can substitute the values from our sketch. Then we can work through this and get that OC squared is equal to 5, which means that OC must be equal to square root of 5. OC, of course, represents the line which connects two centers of our circles. So with this fact, we can use another interesting circular fact. If we have two circles with the same radius, and we pull the common chord for both of those circles, the line that connects the centers of those two circles will always be perpendicular to the common chord. And furthermore, it will bisect the line which connects two centers. So we can easily use this in our favor. First, let's label the vertices of our common chord as P and R, and let's label the intersection point in the middle as Q. If we use the facts from the sketch on the right, we can conclude that the angle at the point Q must be right angle, since the chord PR must be perpendicular to the line OC. And since we know that the length of the line OC is equal to square root of 5, and the chord PR is bisecting this line, we can say that the line QC and OQ both have the lengths of square root of 5 over 2. Alright, so now let's use another circular fact, which states that the perpendicular to the chord drawn from the center of a circle bisects the chord. If you take a look at our sketch on the left, you can see that the line OC is perpendicular to the chord PR, so this means that it will bisect this chord into two identical segments, which we can label as x over 2. Alright, so now let's clear our image once again, and let's take a look at the radius of our semicircle OA. We can rotate this radius to the point P, and if we do this, we will form this really awesome right angle triangle OPQ. So again we can use the Pythagorean theorem, but this time we can say that the leg QP squared is equal to the hypotenuse OP squared minus leg OQ squared, and we can substitute the values from our sketch. Now we can put everything to the square, and then we can get rid of the fractions by multiplying everything with 4, and we can work through this and get that x squared is equal to 11, which means that x must have the value of square root of 11. But remember, this is exactly what we are looking for. We are looking for the length x, which represents the length of our chord, so this means that our chord has the length of square root of 11, and this is our solution. Well, I really hope you guys enjoyed this awesome problem. If you did, do not hesitate to leave a like or subscribe to the channel. Of course, share this video with a person who would love this kind of a problem. And of course, if you found another way to solve this problem, please write it down in the comment section as you always do. And until next time, see you all and take care.